comes a solvent. I told you what the solvent is. This is a piece of tissue from that's been cut up. This tissue is on a microscope slide. It's on a glass thing. The tissue is about 15 microns thick. It's easy to make it flat when it's that thin. And it's stuck to this here. This is on an XY translation stage. That means you can move back and forth and up and down. Okay? That's what we mean by XY. Droplets come out of here. This is nitrogen gas that tends to blow the droplet out. You with me now? Okay? And this droplet hits and splashes. And some of the splash goes into the mass spectrometer. Here's the mass spectrometer in the background. So I hope I'm getting you to see the setup. All the money required is in the mass spectrometer. This is cheap. Okay? This is really expensive right now. I'm trying to get the sense of what goes on. But anybody who has a mass spectrometer can do this. And we're going to now make this thing translate in the X and the Y axis. And we're going to make a chemical map. Okay? And I'm showing you, this is each map element will have a mass spectrum of all the lipids. And we generally see easily 100 different peaks. Each picture element, or pixel. How big is a pixel? It's bigger than a droplet because I can't control the droplet always going to the same spot. The size of the pixel tends to be about 200 microns by 200 microns. To get you to understand that, a human hair in diameter is about 100 microns across. Happily, while this is not the best resolution I would like, and I can talk to you later how to make even better resolution, this is comparable to the knife that the surgeon has. Okay? So it's okay. This will be good enough for what we're doing. And now, here is the actual research procedure. We start by working with banked samples. I have to explain this to you, if I might. Any of you, again, who've had operations or know relatives who've had, or friends who've had operations, you're often asked, will you allow what the doctor cuts out of you to be used for research? Go into a bank. Okay? Some people won't. Then it's just incinerated. My private whatever, my private sewer. Other people are kind, and I appreciate it greatly because the research advance depends on them doing this. And they give this, it goes into a bank, and they're able to analyze what they have in the bank. And we're going to take paired normal with cancer, 62 cases, okay, which we know what we're doing. We're going to then do this DESI mass spec imaging. And there's already pathological staining that's been done. And then we're going to apply a statistical method, which I'll explain to you in a moment. And we're going to actually use this later on to test against actual samples that a surgeon cuts out. First, we're going to train ourselves, then we're going to apply this to show what it's like. Okay? Here is a picture of a piece of tissue, again, from the stomach. And you see this region in red is the cancer portion. This is now normal, okay, tissue and so forth. I can't tell the difference by the coloring. You need a microscope. And here we are. We're making images. Now, I've got to make sure you understand this. This is an intensity scale. See, red's the most intense. Purple and black is the least intense. So, right? And so here's something called arachidonic acid, and it is a fatty acid that has 20 carbon atoms, one chain that has 4 double bonds. That's this type of notation. Here's another one that has 2 chains, 18-0, 18-1. This one means that there's a 1 double bond. And we see different distributions, and you can see the names of these things. How do we know this? As I say, we've identified easily 100 different compounds this way. We do this because we're able to do another technique called Mass spec, or tandem mass spectrometry. What we do is we take an ion, isolate it, and break it up again and see the fragments. And this allows us to be very sure of how to put things together as to what we have. And there's libraries of this stuff with lipids. So a lot of people's work is being used now to know what we have. So we have a good idea what these are. And here's the lasso method, and I'm telling you ahead of time, it replicates pathology findings quite well. This is cancer, this was normal, and look, when we smoothed it, we really got back to the same thing as what they are claiming that they know, not at the time of the operation, but afterwards, quite well, in this type of stuff. And we have maps of these different compounds. Okay? You see, staining, this doesn't give you that much color distinction. And mass spectrometer is giving you hundreds of things to look at. It actually is a much richer chemical information that it's providing. Okay. I now want to explain to you the lasso method. So we're now going to go a little bit into the math behind this. We try to get an answer based on all these different things that we've looked at, all these compounds. Some go up, some go down. So let's get serious about multiple regression analysis and try to figure out what to do. Suppose you have 100 different variables. That's the type of thing I'm looking at. Many of them are really small and just contribute to noise. Okay? To find the two leading variables means you need to test 100 things taken two at a time. You know how to do that math, I hope. Okay, so that's 4,950 tests. If you want, however, to find the three leading variables, you're soon getting towards astronomical numbers of tests. You don't want to do it this way at all. This is not the way to proceed, okay? And instead, this man, Rob Tibshirani, invented a technique called lasso, okay? And he introduced an alternative that constrains the coefficients or equivalently shrinks their estimates towards zero. And it is usual to minimize this type of expression in least squares analysis. Hopefully, many of you have done least squares, seen least squares? One person? More. Okay, very important to learn about this in terms of analyzing data about the least squares analysis. Minimize the sums of the squares. That's what it's doing. And instead of just minimizing the sums of the squares, he makes a side condition in which he tries to also minimize the coefficients. That's lasso, real briefly. Okay? He applies this. We're looking at weights. Some things will go up, some things go down. And I'm showing you in green, which is epithelium, which is cancer, with stroma. And we get a sense of this. And we can actually then do this pixel by pixel as to how well it works. And so the classification system was built to allow a pixel to be classified in one class for which the pixel has the highest probability of belonging. And all 12,480 pixels were tested in cross-validation. We read some things out with probabilities of a certain pixel being classified as shown in green, cancer in red, and stroma in blue. I'm showing you the nature of this. Well, how well does it do? The training set, 28 clear-cut cases. Look, 98% pixel by pixel is what we got by this technique. Okay, validation set. Now these are 34 tough cases. Folks, what do I mean by a tough case? It's when you got cancer and non-cancer going like this. Interpenetrating. Very tough. Follow what I'm saying? It's 3D, not 2D either. Again. Okay, and now we do 9 real surgery cases, and for which the patients have given consent. And in 2 of the cases, with initial disagreement among the pathologists, what happens? In other words, more than one pathologist looked at this, and they argued with each other. Okay? Here's what happened. Our DESI, MSI, that's mass spec imaging, was concordant to the final consensus between the pathologists. Okay? We got it right. Unfortunately, you can't open a person up on the operating table that long to wait days. And so one person went back with cancer because they too soon. These are the realities. Okay? And I'm showing you again how well we did. Prediction results for the 12,480 pixels, analyzed the training set of samples in comparison with the pathological analysis, and that's fine. In cancer, normal, we see what we're doing. We're not getting 100%, but we're approaching it very good, and it's nothing like what was happening before. And we're doing this at a time that's actually faster than these people who freeze stain what's happening. Okay, so here's some initial conclusions of this work. The DESI, MSI, plus the LASSO can be automated, and it can be faster and a more accurate method for margin assessment in gastric cancer surgery. So I believe. And it equals, if not exceeds, best judgment of expert pathologists. We think at Stanford we have some of the best pathologists, and we're telling you this. And what else? It is a valuable complement to existing methods, especially in areas of diagnostic ambiguity and for less specialized physicians in the community. So it could be quite useful. So I'm excited about it. Now, the medical profession is very conservative, and it should be. It's life and death they're dealing with. And so it takes a while to get this stuff adopted by them, but I'm sure it's coming. And we're going to see the mass spectrometer start to show up in the operating room or next to the operating room. I need to, for fun, tell you a bit how things really go, at least in the United States, with regard to research. If I had put in this proposal, that this is what I was going to do, it would have gone to the National Institutes of Health. It would have taken them minimum